Bismillah ar-Rahman ar-Rahim. We are going to start a new concept now, which is electric fields. And electric fields are very important in the electricity, where they are the one who are going to accelerate charges. And when you have charges accelerating through a conductor, you produce a current. So studying electric field is very important. We'll start first of all from the basics. We are going to now do what we call electrostatic, okay? Electrostatic, where the charges are not going to be moving. Later, in future videos, we will do dynamic electricity, where you have a current produced in wires, conducting wires, and so on. So now we are going to talk about charges which are not moving. Now imagine you have a charge here. Of course, the charge has a symbol Q, and imagine you have a positive charge, a big positive charge, and you have here a small, another positive charge, but it is small, a Q0 we call it. We call it a test charge. As you have seen in the previous video, there will be a force on this charge here. There will be a force, and because of the charge are both positives, the force will be repulsion, F on Q0. That force is given by Coulomb's law, K Q0 over R squared, where R is the distance between the two charges, okay? This is R, the distance between the two charges. And you can notice that the force is along the extension of the two charges. The line joining the two charges, the extension of that line give you where the force will be, the direction of the force. Of course, there's a repulsion, and therefore the force is in this direction. I wanted to tell you that I want to do a similarity with another problem here. If you have now a large mass here, M, okay, and a small mass, M small, you know that there will be a force, F, which is called the gravitational force, Newton's law of gravity, right? M over R squared, where R is the distance between the center to the center of the two masses. You can see that, of course, the force here is also, it has a direction. Let's say if this is the y-axis, it will be minus J. It doesn't matter about the direction. I'm interested in the magnitude. Here the force this is called Coulomb's law, by the way, and you should know it from the previous video. Coulomb's law, and this is the Newton's law of gravitation. Newton's law of gravitation that you have seen in the previous course, Physics 101, okay? You notice that there is a big similarity between the two forces. Actually, this force here, I can write it equal to M, small m, the mass, small m, times G, where G is called the gravitational field, okay? This is called the gravitational field. Gravitational field, okay? This is the G, which is, it has a magnitude of 9.8 on the surface of the Earth, okay? So you can notice that the mass, M, which is affected by this force, we put it on the side, and then all this is called, without the minus sign, of course, all this is called a G, the gravitational field, okay? There's a direction, and the gravitational field, as you know, it is directed like this toward the Earth, okay? Similarly here, in electricity here, we can define something now, we can separate now, K, Q over R squared, we separate it from Q0, which is the test charge, which is the same thing as the mass, small mass here. And this charge Q is playing the role of the big mass here, okay? If this is the Earth, then this is the gravitational field of the Earth. If it is the moon, it will be gravitational field of the moon, and so on, okay? So here, as if I have the similarity here, and I call this term here the electric field, okay? The electric field times Q0, okay? That's the gravitational field, and that's the electric field. So as if that this charge here, Q, the large Q, the charge produced around it in this space here an electric field. Okay, so the electric field produced, this is produced by the charge Q, okay? The charge Q, okay? The charge Q, which is here, okay? This type of forces, which are, they call them forces at a distance, okay? Forces at a distance. You see, there is no contact between the two charges, or no contact between the two masses, and there is a force. I can show you now. There's a force. I'm lifting this pen in my hand. This is a force of contact. There's a contact between my hand and the pen. But this force here is a force at a distance, and if any force at a distance needs a field around it. Okay, the particle, this charge needs. There's a field here around it, and we call this field the electric field. Okay. So this is how you explain the electric field, and it is around this charge here, and it is given by, so that electric field there, E, is produced by the charge, is this term here, okay? So if I remove this charge from here, that the field produced by this charge it will remain there, okay? It will remain because it is produced by this charge here, okay? Remember that, huh? So the electric field is produced by the charge Q. Similarly, the charge Q0, we say it's a test charge. It has a very small value, and therefore its electric field is very small, and this charge is very large. Its electric field will be very large, so we kind of neglect the electric field due to the charge Q0, and we take into account only the electric field produced by the charge. So, and these two charges, actually, this charge will start moving if you will start moving along the force F. Okay. So that's the concept of the electric field. So the electric field is something which is produced around the charge, and its effect is seen when we bring a charge Q0. There will be a force on that charge. It's called the force at a distance. Okay. Now, so if you remember that this charge is positive, okay, you can see the charge is positive, and therefore the force there's a force here, okay. The force and the electric field will have the same direction. So there will be, if I want to draw the electric field here, I have to draw it in the same direction as the force. Okay? If I go to a point here, now this electric field is produced by this charge here. So if I want to draw the electric field at this point, I don't need to have a charge. There will be an electric field in this direction, E. Okay? Produced by this charge. At this point here, there will be an electric field, so you extrapolate and you go like this. That's the electric field produced by, as you go closer to the charge, the electric field becomes larger because R squared, you see the R squared, as you go away from the charge, the electric field becomes smaller. As you are closer, R is small, the electric field will be large. Okay, so these are the electric field lines. It's a vector, it has direction, okay? So the positive charge, if you take a positive charge like this, okay, the electric field will be directed, we say directed radially outward. You can see them, huh? They're directed radially outward, and its magnitude depends on what? On the distance R between the charge and the point where you want to calculate the electric field. If I want the electric field at this point, it has a magnitude given by this kq over R squared if you want to calculate that electric field, okay? So if you take a negative charge now, let's come on the side here. I take a negative charge, and we have also our test charge, okay, which is here. Let's take our test charge here. Another test charge is Q0 is positive, and our charge here is negative, okay, charge Q, okay. There will be a force on the test charge here. Let's draw the direction of that force as we did there in green, okay. Since the charges are opposite, the force will be attractive, will be in this direction. Okay, a distance R. The distance R is the distance between the two charges. Distance R. So there will be a force, and that force again is K, Q, the charge, Q0, the test charge, over R squared. Okay, and that should be equal to what? Should be equal to Q times E. Same thing. Q times it should be equal to E times Q0. Okay, but our Q0 is also positive. If Q0 is positive, then F and E will have the same direction as we did here. You see, Q0 was positive, so this vector and this vector will have the same direction. You can see F and E. Here, my electric field direction will be the same as the force because our test charge is positive. Okay, so E and F will have the same direction, so the electric field will be in this direction here. So, because E is a vector, F is a vector. This is multiplied by a scalar which is positive. So E and F will have the same direction here. So the force, the electric field will be radially toward the charge. If I go to this point here and I want the electric field, it will be radially toward the charge with a larger magnitude because we are closer to the charge. And again, that electric field is KQ over R squared, okay? That's the electric field for a point charge, okay? This is a point charge, let's say, okay? So, if you go here, for example, I want the electric field, the direction of the electric field here, I'm drawing, it's important to draw the direction, it will be inward, okay? So we say for a positive charge, let's write it here, for a positive charge, the vector E is radially inward. Inward means toward the charge. For a negative charge, if the charge is negative, I'm talking the charge Q here, which produces the electric field, okay? Negative charge, okay? The E is radially inward. Inward means inward. It should be outward. Sorry, again. So this should be outward, as we can see from the figure here. It's outward, okay? The electric field is outward, okay? And here it is inward. Inward means toward the charge. You see the direction of the electric field is toward the charge. And this has nothing to do with the charge Q0. You have to look at the charge of the sign of the charge which produced the electric field around it, okay? So that's the electric field for a charged particle. So a positive charge, let's summarize, a positive charge will produce an electric field around it, and that is called the electric field, okay, around it, which is radially outward. A negative charge will produce an electric field around it, which is radially inward, toward the charge, okay? So and its magnitude will depend on what? On the magnitude of the charge and the distance between the charge and the point where you want to calculate the electric field. Because R is important here, the distance between the charge and the point. Okay, so that's what it is about the electric field. Let's now talk about something called the superposition principle, where you have many charges, okay? Superposition principle. This is now we have, of course, this it is important to note the electric field for a point charge. This is important. This is the formula for electric field for the point charge, okay? It's KQ over R squared, okay? If you have now many charges, superposition here means you have plus Q1 here, minus Q2, okay? Another charge here, Q3, which is positive, okay? Q3, and another charge, let's say another charge Q4, okay? Charge here Q4, negative charge Q4, and I want to find the electric field due to these 4 charges at a point P here. Okay, this is point P. So what do you do to find the electric field for that charge? First of all, you take them one by one, okay? So the electric field due to this charge here is radially outward. So this is E1. The charge for this, the electric field for this charge here will be radially inward toward the charge. I call it E2 because it's produced by Q2 and negative charge, so the electric field toward the charge. You go to E3 here, same thing. Okay? So you put your pencil here and you look at the charge. It's positive. You go outward, radially out. This is E3. Okay? And then you go to Q4. Q4 is what? Is negative charge. You draw the line here joining the charge and the point, and it will be radially inward, E4 like this. Okay? So now you have to find E net. E net, the electric field at point P, will be the sum, vectorial sum, not the algebraic sum, the vectorial sum of the 4 vectors. If you have more than 4 electric field, you have more. If you have more than 4 charges, you will have more than 4 electric fields. Okay, so now you draw an XY axis. Okay, and then you have to, now the way to do it is to find the E at point P along the X axis, So you decompose every force, every electric field along the x-axis. You see that these are the components. This is the component of E1 along the x, component of E2 along the x, then a component of E3 along the x-axis, and component of E4 along the x-axis. And we call it this E at point Px. This is the x component. Then you do the same thing for what? For the y component. So you have E1 y plus E2 y, the y component of the second vector. Then because these are vectors, so you have to find their components along the x. You need angles there. You need to know the angles, of course, between the x-axis and so on. Then once you get the numbers here, you can calculate here. Let's calculate here what is EP. E, the electric field at point P, will be the square root, okay, of EPX squared plus EPY squared. So you take these values here, whatever value you get here, and whatever value you get here. Of course, the electric field has a units. You can see it here. From this is the electric field has a units of Newton over Coulomb. Okay, so you put the units here of Newton over Coulomb. The SI units for the electric field is a Newton over Coulomb. So you take these two numbers here, you square them, and you put them here to find the magnitude of your electric field, net electric field at point P. We call it the resultant electric field. If you want the direction of that electric field, the net with the x-axis, you can find the tan inverse of what? Of EP, E at point P along the y divided by E at point P along the x. We will do examples later, and this number here, the EPX will go here and EPY will go here. We divide them, you take the inverse, you find the angle. This is the angle between the electric field and the x-axis. Thank you. Okay, let's continue now and see how to draw something called the electric field lines. Imagine now you have a positive charge here plus Q and another negative charge here minus Q, and let's draw what we call the electric field lines. You know that by now you know that a negative charge, the electric field always are toward the negative charge and away from the positive charge. So look at me how I'm going to draw these electric field lines. There will be a line here where the electric, this arrow indicates the direction of the electric field, okay? It will be something like this, okay? And like this here. There's a symmetry in the problem, something like this, and there is another one here, okay? And then they start coming from higher, okay? And going here, going out from here, and going here, going in here. These are called electric field lines. Let me write down this. Okay, we call electric field lines, okay? Now, at any point, if I want to calculate the electric field, to know the electric field, direction of the electric field at this point, we take the tangent. This is the electric field net, because I have two charges, remember? So that's the electric field net at that point. At this point here, the electric field will be tangent to the line. So, the electric field at any point is tangent to the electric field lines at that point, okay? If you want the electric field at this point here, it will be like this. At this point here, it will be like this, okay? So these are, in black, are the electric field vector. In blue, are called the electric field lines, okay? So if I take now, on this side here, a positive charge Q with a positive charge Q, okay? Now remember that positive and positive, the electric field will be coming out from it. So how do you draw the electric field lines? There will be a line like this, a line like this, one like this, one like this, and so on, okay? So they will be going out from the charge. They will be going in this direction like this, okay? So these are the electric field lines from positive charges. And you notice here, there's no electric field. We will see later why there's no electric field at that point in between the charges, okay? So these are, and the electric field, if you want to draw the electric field vector itself, not the lines, tangent again, the tangent to the lines. Tangent to the lines, everywhere. Okay, that's the electric field at different points. Okay, so you look at the electric field lines, and at that point you take the tangent to find the electric field at that point, okay? So that's the electric field line for different two charges close to each other. Let me now show you the electric field lines for an infinite, a large sheet, a large conducting sheet. Okay, this is a large charge sheet. Okay, here in this case, the electric field, of course, we have to put the sign of the charges, otherwise you cannot know the direction of the electric field, because you have to put now in positive charge, the electric field will be going out. Okay, these are the electric field lines, and at the same time, this is the electric field itself. Okay, when the lines are parallel like this, the electric field lines and the electric field are in the same direction, not like here where you have to take the tangent. Here there is no tangent here to take. Okay, that's the electric field E. I'm going to write E. So E and the electric field line are in the same direction. That's the electric field. Okay, you can see, we say when you see lines like this parallel, we say that the electric field here is uniform. Okay, electric field is uniform. Let me write this in red because it's important concept. Uniform. Okay, we will see later. Later you will actually calculate the electric field for these sheets. Okay, what happens if my large sheet has a negative charge on it? It's a sheet, but it has a negative charge on it. You will expect that the electric field lines or electric field will be parallel lines, but they are going inward toward the charge, as you expected. This is the electric field lines. Okay, and the electric field at this point here will be in this direction. Okay, that's the electric field due to these charges here. Okay, similarly on this side, the electric field will be in this direction toward the negative charge, and the electric field for positive charge will be what? Will be away from the electric field, from the charge itself. Okay, so that's about electric field lines and superposition principle and electric field for a point charge. Let me remind you now about electric field for a point charge. Okay, again we go again to electric field for, let me write it down here in detail, for a point charge. So my charge is a point. Okay, so my point charge looks like this, like we have drawn before. So we have a positive charge here, and away from it we have a negative charge here. And we want to draw the electric field lines. Again, electric field lines are pointing what? Radially outward. And this is not uniform electric field, of course. It's not uniform. Electric field at this point and this point, they are not the same. Here, electric field at this point, at any point here, is the same. And we say a uniform electric field. Here, the electric field E1, if I call this one E1 and I call this one E2, I'm sure that E1 is greater than E2 in magnitude, okay? Because E1 is closer to the charge. And the electric field, its value, or it's K Q over R squared. What is R here? R is a distance between the charge and the point where you want to calculate the electric field. If I want the electric field at this point here, this is my R, okay? And it is positive charge radially outward. And its magnitude is given by this. For a negative charge, of course, the electric field will be radial, of course, radial, like this, like before we did, but it is inward, radially inward, okay, toward the charge, okay? That's radially inward. And it has the same magnitude. The magnitude is the same, however, the direction will change according with whether it is positive or negative charge, okay? So the electric field at this point here will be in this direction. That's the electric field at that point, okay? One thing important is something called the electric field line density, okay? If you draw here a sphere, this is three-dimensional, you see that the distance between the lines is very close, okay? And therefore, it tells you that the electric field is strong there. If you go to another sphere, bigger sphere, you see that the distance between the two lines is large, and the electric field there is weak. So whenever you have too many lines, electric field lines, very close, this is E, we say that is the strong electric field here. If you have lines away from each other like this is weak. E is weak, okay? E is here weak. electric field, okay? So is strong, okay? Here electric field is strong. So the density of the electric field vectors, okay, it gives you an information about the strength of your electric field. Here the electric field is strong, here it is weak, because the distance between the electric field lines is large. Okay, let's continue now. We want to talk about electric field due to a dipole, electric dipole, of course. Electric dipole. Example of electric dipole are the molecular dipoles, such as water molecule or HCl or HF, and there are many other examples of electric dipole which are available in nature, such as these molecular dipoles. Let me now. I want to calculate the electric field to this dipole. So the dipole generally there is represented like this. I'm going to draw for you a dipole, okay? A dipole will be two charges here, a positive charge and a negative charge, Q, and they are equal, okay? Equal in magnitude and opposite in sign, okay? Positive and negative charge. The distance between these two charges, I call it D, okay? D, the distance D. Okay, and this is the origin of my. I'm going to take an axis now. Remember now, I'm going to take an axis. I call this the z-axis, and okay, the z-axis. So I need the distance d between the charges. I know the charges here, and I want the electric field at this point on the axis of the dipole. So on the axis of the dipole, okay. It's important to have this in. If you move from the axis of the dipole, the result I'm going to show you will not be valid, okay? So I'm talking about on the axis. As you know, as we have seen many times, okay, let me put this positive charge clear here and negative charge here. There will be two electric fields. One will be due to the positive charge, and it will be outward. I'm going to call it this E plus. I hope you agree with me. Plus is for the positive charge, and there will be a negative. The negative charge will produce an electric field here, and it will be smaller, and I call it E negative. Why the magnitude of the E negative is smaller than the magnitude of E positive? Because of the distance. Here, the distance is from here, from the charge to this point, is smaller than the distance from this charge to this point. If the distance is smaller, it means the electric field is larger. So the positive charge will have a larger electric field. So the net electric field will be in which direction? The net. Remember the superposition principle? I have two charges here. So the net will be upward. When you subtract them, you have to subtract them here. So E net will be in this direction. E net will be upward. Okay. So E net, okay, will be E plus minus E minus. Sorry, as a vector like this, but in magnitude, if you want to go to the magnitude now, magnitude of E net will be E plus minus E minus like this. This is a minus sign, and this is E minus for the negative charge, okay? Positive charge, negative charge, okay? So let's now do some calculations now. I'm going to use this equation here, okay? I'm going to call this distance from here, from the center to this point, I'm going to call it Z, the variable Z. Z will be changing, okay? Depending on the point where you are. D is fixed. So let's now E plus K Q over what? Q positive, of course, is Q. Q over what? Over R. What is R here? R will be this distance here. Will be Z minus D over 2, because remember, D over 2, everything squared. There's a minus sign due to the direction of E minus sign, and then K, Q over Z. What is the distance now between this charge and the point? You see, Z is from the origin. This is the origin. And then you have to add D over 2. So Z plus D over 2 squared. Remember now that D, the distance D, is very small compared to Z. This distance is very small compared to Z here. We are far away from the dipole, okay? So I'm going to do something called an expansion. KQ, I'm going to bring this up. Z minus D over 2 to the power minus 2 minus KQ Z plus D over 2 to the power minus 2. I'm just lifting, raising this up with the power minus 2, and then I'm going to expand this because of this condition here, okay? So this will be KQ Z plus the 2 will come down here. It cancels this 2 here, so it will be KQ Z plus D. Okay? So let's now bring this Z outside. Okay? KQ over Z squared 1 minus D over Z everything squared. Okay? There's 2 here, 2D. Minus, the minus sign is from the direction of the electric field, as we can see here. K Q over, I'm going to take here again Z squared outside. Then I will have F1 plus D over 2Z. Like this. Okay? To the power 2. Then I'm going to take this up and use this fact here. Okay? So I will have a K Q over Z squared 1 minus D over 2Z to the power minus 2. The first one. Then there is a minus sign. K Q over Z squared 1 plus D over 2Z to the power minus 2. I'm just raising this up and raising this up and putting the minus 2 here in the power, okay? Now I'm going to expand this. We say an expansion. I'm going to bring this 2 down here. Eh? So it becomes K. This is the expansion that you have seen in math, maybe 101 or 102. Okay? Is 1. So it will be a plus. This 2 cancel. It will be plus D over Z for the first term here. Minus K Q over Z squared 1. There will be a minus sign here. Eh? Minus D over this 2 cancel this 2. There will be D over Z. Okay? Now I open the brackets and I multiply. Okay? So this term here, this term and this term will be there, but this term and this term will cancel. So what do you get at the end? Your E net magnitude. Eh? E net in magnitude, not direction. Okay? I'm talking about magnitudes here. Okay? So when you open the brackets here, this term is going to cancel this term. This term is going to have, so KQ over DZ cube plus KQ over DZ cube. So it will be 2K cube D over Z cube. Okay? That's the answer here. That's the electric field at this point due to the dipole. Okay? At this point, the distance Z should be larger than the distance D, the distance between the two charges. Okay? Is it the dipole? Remember, the charges are equal and the distance between them is very small. And I give you an example of a dipole that exists in nature. They call them molecular dipoles. Okay? So 2K D times Q, I call it P. They call it dipole moment over Z cube. So P here, let me write down in blue here. P is Q times D is called the dipole, electric dipole moment. Electric, because there will be a magnetic dipole moment later. Okay, dipole moment. We call it electric dipole moment, and it has direction, of course. It's a vector, of course, and I'm going to put it as a vector. Okay, it is directed from the negative to the positive charge. So its direction is in this, like this. It has the same direction as electric field. Okay, so this is the direction of P as a vector. It will be from positive to a negative charge. I'm going to write this result here is important in red here because it is an important result. It says that the electric field of a dipole is given by 2K P over Z cube. Remember that here it is Z cube. If you have a point charge, it will be this R squared. Okay, this is a cube here. That's the electric field due to an electric dipole when your point is far away. Now, if you go down here, the electric field also will be pointing upward. Okay, It will be pointing upward. So it is always pointing upward, the electric field. And E and P will have the same direction always. You can see it here. E and P will have the same direction. Of course, the units here is always Newton per Coulomb, even though you have this squared here. And electric dipole has the units, which is Coulomb meter. Okay, these are the SI units for the dipole, electric dipole moment, and the SI units for the electric field. Later, we will see how this dipole moment will be affected by an external electric field. There will be a torque, there will be energy, and so on. And this will be done in the next video. Thank you.